Okay, so our next presentation is supporting OpenSSL 3 providers in an architecture and restrictive OSes by Alexander Zaslavsky. How about that? All right, and with that, as long as I hit the slide button, right? There you go.
Thank you very much. Thanks, Loren. Hello, everyone. Just look how does it work. Okay. So basically, OpenSSL version 3 introduced two great additions. One of them was FIPS provider, FIPS-3 provider. I'm sure that a lot of you were waiting for this addition. And the other great addition was providers architecture, which basically, it's a great design, and it allows even our third parties to just follow the APIs, generate their own provider, supply it to our customers as a shared object. Our customers don't need to recompile, relink anything. Basically, we just can give them the library, and it's all great, right? But apparently there is a small challenge here, and these two concepts collide. And basically, if you want a FIPS-3 provider for iOS, and specifically when I'm saying iOS, I mainly speak about deploying application to App Store, it becomes a challenge. And in this presentation, I will try to explain why right now the current solution doesn't work, and basically we had to do it internally and how we managed to solve this problem. Okay. And maybe just one note, maybe it's easy to say that iOS doesn't support dynamic loading, but actually for quite a lot of years they do support dynamic loading. They just support it in a bit different way, and it's essentially a trade-off between convenience, as I mentioned to you. You know, it's very easy to deploy a new library, but it's a trade-off between convenience and security. As we all know, bad guys also like to deploy different DLLs and play with different path locations, and Apple chose more secure way, and I totally agree with them. Okay, so what I'm going to speak about. So basically, I'll start by speaking about solutions that doesn't work. I researched a lot. I looked at all kinds of attempts of people sharing their idea over GitHub or other repositories and trying to find easy solutions. And unfortunately, doesn't look to be a very easy solution to solve it. But I wanted to give you just a recap, so at least you will know that it doesn't work to follow that path. And then I'll try to build over basically a default provider and how some solutions can actually lead us to a way when we eventually can build a FIPS provider as a provider running on iOS with happy customers deploying it with their application to Apple Store. Okay. And yeah, I'm sorry, it's fairly technical, so ask me any questions or anything. I'll try to explain if it's some of the terms I'm using are like easy to me, but maybe. Yeah, so as I mentioned, some of the solutions I saw on the web. Okay, let's just clone the OpenSSL 3 repository. Let's just change the compiler to use the toolchain compiling it for iOS, and probably we'll get something, right? That's how it worked in previous versions. So not exactly. As I mentioned, it's not that Apple Store doesn't support dynamic loading. They do support it, but they require the libraries to be signed, and basically if you just generate a dylib or shared object, you can't deploy it to App Store. Okay, so that one won't work, but how about frameworks or XE frameworks? Apple did come with a solution to enable developers to write dynamic libraries or static libraries and to be used basically as part of someone who really wants to not to just deploy their application, but also to have libraries So they have a solution for dynamic libraries. Okay, so, and you can think in this context like framework or XC frameworks is very similar to an ordinary library we are used to in other operation systems. The challenge specifically with FIPS is that the way FIPS model is implemented is that it requires to be validated, verified basically that the model we are loading is actually the model we are expecting to load, right? So we have all this HMAC logic, which is basically being run on the binary, on the DLL file, and it's verified that actually, okay, everything is good. The tricky part with Apple is that once we give our customers a library, the OpenSSL or whatever library we provide them, and application users try to take this library and deploy it to the Apple Store, this library is going to be re-signed with a certificate of a customer, of a user who actually deploys this application. So they're going through the App Store deployment process, they're going to change the binary. They're going to change the library binary, and everything we did previously with calculating HMAC and providing them with some value, it's going to break. Okay, I hope it makes sense. I'll try to address it in a few next slides, but just taking basically a library compiled as a shared object and converting it to XC framework won't work. Okay, so maybe dynamic libraries is great, but maybe we can switch to a more easier approach of creating a static library and provide our customers with just a static library. They can link it during the development time, but still, maybe this will actually work in iOS. Yes, but here comes the tricky part of actually, we have libcrypto, we have libfibs, and if you look, there's almost 2,000 symbols which are common between libfibs and libcrypto. And kind of makes sense, right? In FIPS library, we still use the same primitives, we still use RSA, we still use elliptic curves, but we have some small additions to the logic, which saying basically, okay, if you're generating RSA keys, make sure that these keys are actually matched, rather the public key matches the private key. And we use all of this if-def FIPS module. So the symbols will have the same names, but unfortunately we'll have slightly different implementation. And if you just try to combine them into one huge library, you might get the wrong implementation, and you might get not exactly the FIPS implementation. So don't do it, or at least do it very carefully. Okay, so this is some of the pitfalls I noticed when I started working on this project. So what actually does work? If you take the default provider, which is part of libcrypto.a, and you compile it for iOS, and you wrap it into XC framework, this is the Apple part, and you just sign it, and you write a dummy application and you deploy it to App Store, this part actually does work. So it gives hope. And I provided some details, but basically, yeah, I'm using the toolchain for iOS. I'm using a way to create XC framework with Xcode build. And yes, I have to sign everything. This is how Apple works. It's not just a dummy library. I have to provide my credentials so I can deploy it to App Store. So, okay, this actually works. Okay, so can we do it with FIPS provider? Okay, let's try. Let's try actually to merge libcrypto.a and libfibs.a into one static library. And as I mentioned, if you're an example in code, it's a bit tricky because there are a lot of symbols which are common. But we can create a list of them. You will get around 2,000 symbols. And then basically, maybe we can just rename them in the FIPS library, so we won't have the conflicts. And I think I have it in the next slide, so I was running a bit fast. But okay, so we can use NM, right? And we can find all the symbols in libcrypto. We can find all the symbols in libFIPS. We can write some Python script to find all the shared ones. And then basically we can use some of the macOS object copy tools, which basically allow us to say, okay, in FIPS library, whenever you see an object file AES CBC encrypt, just replace it with FIPS underscore AES CBC encrypt. So we just remove the conflicts, okay? And basically, yeah, I'm changing here the libfips.a library. I'm creating a new one by changing the symbols. But at least the linker will know to use the right implementation. I hope it makes sense. Okay. I should have finished my presentation by now, but I guess. Okay, I'm doing fine with time. The other part we also need to handle is basically what do we do with the integrity check, right? So the current OpenSSL implementation is basically saying, okay, before we load the actual library, let's calculate HMAC on the binary. Let's compare it to what we have in configuration. Let's make sure that they are the same. And if they are the same, this is great. I can still change the configuration, but I think it comes from the hardware times where actually this part was hard-coded. So yeah, but this is how it works. And unfortunately, this part doesn't work well for our libraries generated for iOS. But it seems like NIST actually thought about it, and there is implementation guidance 9.10, no, 3. It's actually in FIPS-2, but I believe it's also relevant for -3 as well, which basically says if you have to use a static library rather than dynamic library, you can do the same check, but in memory. So you have to look at the text segment, at the code data segment. It's a bit more tricky, but basically it's the same, right? Either we check it on the file or we check it once the module already in memory, but we still, and actually it's much better to do it once the module in memory. So we have this option. So basically what we can do is once we create this library, we can create a dummy object file at the beginning, at the end, put some pointers and say, okay, this is where everything starts. This is where the text segment actually ends. And we can take these pointers and calculate basically HMAC SHA-256 on memory. Pretty much the same implementation, just I'm using pointers and not files. And I also, FIPS says that I need to do it both on the actual code segment, but also on all the static variables which are in the data segment. So I need to do it on both parts of memory segments. And basically, if I implement this logic, I have a new validation logic which can run in memory. Okay, I also mentioned that it requires several compilation, but it's just internal detail maybe. So basically, in the first run, if the value doesn't match, we just put the expected value, and then we hard-code the value in our code. And basically, the specific hard-coded value is outside of the FIPS boundary, so we are allowed to do it. Okay, and then you have a FIPS valid process. Okay, and I guess I'll stop here. Maybe I'll just say that basically this is not the entire implementation, but I think these are the two main topics where we felt our most challenges are, and I wanted to emphasize, and I guess I need to say that if you need a full implementation and you don't want to implement it, you can just come to us, but yeah. Yeah, questions?
That might have answered my question. I was going to ask if you're going to contribute this back to the open source community, because this seems like a lot of work.
I think we are thinking about it. My CEO is here, so you can ask him as well. I try to contribute as much as I can by just giving the ideas. We're still a commercial company, but I think that eventually, I hope that eventually we will do so.
Gotcha.
Hi, Simon from Red Hat. We do something different. We also embed the HMAC into the binary, so we have to deal with a binary that's different from what you have initially, but you seem to do memory HMAC. How do you deal with address randomization? Do you just disable address randomization, or I guess doesn't have it? How does it work there?
Yeah, we also were a bit concerned about SLR, and what we saw so far is basically the randomization only happens basically on the start of the segment, but all the code is kept in the same block, so we haven't seen any issue so far.
So you don't have relocations, or you're able to do the check before relocations?
We have it just in one chunk.
I just very interesting idea. So I just like to confirm. You said that you finally successfully load the provider into iOS, right? Through XC framework. But this is for the specific app, or can used by all app, right? In this form.
If I get the question correctly, yeah, we create an XC framework out of our library, static library. We don't do any dynamic loading, basically.
Oh, users using the
we provide a static library.
But this not benefit from OpenSSL 3 provide framework, right? Yes.
Yeah. But again, from security perspective,
okay.
and the way iOS works, so far it seems like this is the only solution which actually works for us.
Yeah. Okay. Thank you.
I was just wondering why you couldn't use the Apple signature as your integrity check. Aren't they using FIPS-validated algorithms?
Yeah, it's a great question. We try to adhere to FIPS specification, and basically they are saying that we need to first validate our own HMAC logic, and basically we try to follow as much as we can the existing implementation, only change what we have to do. But yeah, eventually it would be the best idea, I guess, to use what signature Apple is using.
Hi, great work so far. When you're talking about what didn't work and eventually what you did work, one thing I didn't notice on here, contemplate, is the default providers embedded in libcrypto and FIPS is outside. Did you consider taking out the default provider and sticking inside the FIPS and the base so that there are no symbol conflicts? Setting aside the integrity HMAC, but just avoiding the symbols by swapping out which one is included in libcrypto.
So actually, libcrypto has a lot of logic which we actually need for the FIPS provider, right? All the EVP layer, everything is part of libcrypto. So just taking it out, we also consider this part, but we felt that just renaming the symbols can be a much easier solution.
Right, all that stuff that's in default that's not in FIPS is in base. So FIPS plus base equals default for all intents and purposes. So you'd have to shove both of them in there. Just curious if you'd looked at that.
We thought about using just the base and FIPS, but we felt like still, encoding and all this part is still part of default provider. So we felt like we probably will need some of the logic in default provider.
Thank you.
Okay. Thank you.
All right, everyone. So we're going to continue on with the next presentation about post-quantum key management systems. So this is Yogesh Swami.
So I'm Yogesh Swami. I'll be talking about PQKMS, which is a post-quantum key management system. And the first question that most people want to know is like, why do we need like another key management system? Because there are already quite a few key management systems out there in the cloud. And to answer that question, let me go back a couple of years in time. So I was working with a friend of mine who is a data scientist. He does like federated learning. He does things with like federated learning. And there he will aggregate data in the cloud. And he was trying to use Intel SGX to encrypt that data, store it into a data lake and things like that. And the problem that he would face is that every time his VM would reboot, his data would become unencryptable because Intel SGX, it uses like a chip-specific key, which is like CPU-specific. And in the cloud, when you reboot the VM, it runs on a different CPU, so he could not decrypt the data. So he asked me like how he can solve this, and I suggested casually that he can just use like one of the KMSs. He can put like a master key in one of the KMSs, and then he can decrypt his data using the keys that are in the KMS. And to that, he asked like a very interesting question that what kind of guarantees can he expect from the KMS? So of course, Intel SGX, it gives you like some well-defined guarantees. You may not like those guarantees. They may not be sufficient for your needs, but at least it gives you like a well-defined set of guarantees that can be validated. And I didn't have a good answer to that question because there are like lots of KMSs, there are like lots of documentation. But if you ask like which KMS gives what kind of guarantee, that information is typically missing. So we went out and like we started digging into the different KMSs and what kind of guarantees they provide. So let me first go over like what we typically have available in the cloud at the moment. And then I'll present like what we are trying to do, which is somewhat different from this. So this may not be representative of all KMSs, but this is by and large the case that typically you have like a HSM-backed key management system. And these HSMs are like embedded devices connected to your host OS. These embedded devices have their own CPU, they have their own software, they have their own compilers, they have their own set of tool chains. And these tool chains are like optimized for that platform. So these tool chains may not have like, may not be up to date in terms of like static analysis, in terms of like dynamic analysis. They have like compilers which are like maybe 10 years old, maybe they don't adhere to all the C and C++ standards because they were designed like 10, 20 years back. And typically, the way these things work, they have like a domain key, which is like the root of trust of that HSM. This domain key is claimed to be inaccessible to anyone, including the user or the admins. And you have a two-tiered interface. One set of interface is for managing these HSMs, which means that people who are like sort of working in the IT, they can do things like backup restore. They can create a cluster of HSMs, things like that. And then you have the actual user who actually generates keys inside these HSMs. And since the storage space within the HSM is small, the keys that the users create, those keys are encrypted with the domain key and stored outside of the HSM. And in some HSMs and in some KMSs, you have support for attestation, which would say that you are actually talking to a HSM. But these attestations, they don't include the actual security or the software supply chain that was used to build these images. So if I cannot verify sort of what is the code that was used to build the image, the attestation is not that meaningful because the attestation could just be, it's just a signature on something. And that signature alone doesn't tell you anything like what kind of code actually created that signature. The other problem is like the activities of the admin, the things like creating a domain, creating like a cluster, that information is not sort of visible to the user. So the admin could be adding 10 new HSMs to the cluster, but you will not be able to see it, even though there might be like audit logs and things like that. So the first set of problems that I would say with existing HSMs is that you have like a domain key which is within the HSM, which the user does not have direct control over. So you don't know who has access to this domain key. Of course, there is claims in documentation. But if you have like a breach in your HSM, if your software that you're running on the HSM is buggy, and someone can get into the HSM, then all the keys will get compromised. The second set of problem is that if you have like a cluster of HSMs, you need to synchronize the root key, the domain key, all across all these HSMs. And because KMSs manage these things behind the scenes, the admin user is supposed to synchronize the keys across all these HSMs. And this synchronization happens manually. So a quorum of admin users will authenticate. They will they will sort of wrap the root key, take it out of the HSM, move it to a new HSM. But it's not clear who the root of trust for these transactions are. So whoever is the root of trust of these communication transactions, they can potentially do like a man-in-the-middle attack. Really trivial man-in-the-middle attacks are possible here. And I've looked through the documentation. I have asked like ChatGPT, and no one seems to know like, what is the actual root of trust for all these things. So my guess is like these things are like probably not documented, or like it's probably not fully thought through, or people don't want to disclose who the root of trust is. It's also unclear if the cipher suite that is being used across these HSMs, whether that is like post-quantum secure or not. So in the post-quantum world, we of course want to have like a post-quantum secure exchanges, and we want them to be like at a compatible level of security. So as quantum cryptanalysis improves, these parameters, like what key sizes you should be using, those things might change as things improve. So we wanted to have like a system which is like agile to like changes in the system, which is agile to like post-quantum cryptanalytic attacks. But one of the biggest problems with all of this is like all these operations which are happening behind the scenes, they are invisible to the customer. So if you want to make a guarantee about the system, you cannot make that guarantee directly, because all these things are fundamentally hidden from you. The third set of problems that we have been encountering is that most people are like, so HSMs and KMSs, they are designed to protect keys. But what most people want is to protect their data. So for signature, protecting keys might be fine, but for actual data in the cloud, what you want to protect is your data. And you want to protect the data which requires like chaining or composing different operations at a block level, so that you can terminate your TLS inside the KMS. Then you can extract PIIs while everything is encrypted. Then you might want to do some format preserving encryption or tokenization to some parts of that data. And then you might want to combine all of this and put it encrypted inside a database. And none of the cloud KMSs, at least the ones that I have looked at, none of them allow you to actually compose these things while keeping the data always encrypted. Of course, the role of a KMS is to protect the keys. So having like added functionality like extracting PII or doing like some additional things, that can actually breach the security of the system, because now these things might end up having access to the keys. So there is like a sort of a balancing act that needs to happen here, is that the new components that are coming in the system, they should not be destroying the security of existing components in the system. And so we were asking the question, like, what kind of guarantees basically all these KMSs provide? And most of the guarantees that these KMSs are providing are at entirely at a system level. What I mean by that is that if you have a breach in your HSM, a session compromise, so someone breaches the session, you have like universal compromise of all keys in the system. And so this granularity is at like a very low level of granularity, like it's not very fine-grained. The other problem is like there is attestation in some of these HSMs and in KMSs, but this attestation is without any verification of the software supply chain. So if I cannot verify like the code that actually generated the attestation, I don't know what that code is attesting to. So it's quite important to have the ability to verify the software supply chain that was used to build those components in the KMS. And finally, there is like lack of transparency. Of course, there is documentation, but documentation is sort of, is not proof. And what we are trying to do is like, we want to give like guarantees which can be sort of like proven. So which you can actually take a look at, you can say like, this is right, this is wrong. But not just like read, because documentation is more like a wish list, not so much like what it actually does. And finally, we wanted to allow people, and so this is like the most widely requested feature, that people want to compose things into the system. They don't want to just have like, they don't just want to protect their keys, they want to actually process the data while it's encrypted. At the same time, they don't want the code that they are bringing in, so data scientists use like Python a lot. You don't want to give like your whole Python VM access to all the keys in your system. That would be like terrible. And finally, our motto sort of is that you cannot trust what you cannot verify. So everyone knows about like you can't improve what you can't measure, and I think the corollary of that for cryptography is that you cannot trust what you cannot verify. So we started building a KMS with these criteria in mind, and our design goal was that we should provide better isolation in terms of cryptographic guarantees, not just system security guarantees. What I mean by that is like we should assume that someone will break into the system, there will be bugs into the system, people will be able to breach the session. But in spite of that, a simple breach of the system should not compromise the entire system. Similarly, we wanted to have like verifiable guarantees in terms of if I'm signing something or if I'm verifying the attestation, I should have the ability to look at the code that actually will finally run into the system. So it's not just enough to get like attestation, I should have a mechanism, or the system should give me ways so that I can verify what code was used to generate these attestations. And finally, we definitely wanted to have like post-quantum support, because I think that's required at this point, I would say. So for encryption, we of course want, like for encryption and key exchange, we wanted post-quantum support. For authentication, it's a preferred mode, because authentication typically is not that long-lasting, so you don't have like problems with like someone forging your signatures 30 years down the line. And we also wanted to have like flexible composition and delegation. And so we're at a point in history where we have like an amazing set of tools, cryptographic tools to deal with this problem. On one hand, we have like FHE, which is like fully homomorphic encryption with verifiable computation, where every bit of your computation is encrypted at all times. So you can do completely encrypted computation in the cloud. The downside of that is that the output of your computation will also be encrypted, so it typically is not very useful. So you have to do some thresholding and things like that. On the other hand, we have like isolated, cryptographically isolated RAMs. So here your whole RAM is like encrypted, so your whole VM is encrypted by the processor. And apart from that VM, no one else can access that RAM. So this is like cryptographically isolated RAMs. Somewhere in the middle or towards the right, we have Intel SGX, where you can do further partitioning of each application. And somewhere on the left, we have MPC, which probably doesn't belong here, but I put it here because of garbled circuits. So we have like a lot of tools available. Unfortunately, most of these tools are not being used, and these tools can give you like really good guarantees. But the problem is like you have to actually sort of have a demand to build all these things. And most people, it seems, are like quite happy with except for like the cryptocurrency world, where most of our customers are coming from. They are quite demanding about all these things. They don't want to trust the cloud, which is a good thing. So the solution approach that we have picked is to use like MPC and thresholding for authorization, so that we can have like fine-grained protection for each key, and use Intel SGX, which helps with like composition and things like that. And so the way our system works is basically, the first thing that we wanted to do was like, we did not want to have modules in the KMS which the user has himself not signed, or which the user itself has not like verified. So the way our system works is it has like a set of enclaves. These are like task-specific enclaves. So there could be like a web gateway, there could be like a pairing-based crypto, or there could be like a module learning with errors-based system. There is like elliptic curves, and all these enclaves, they are like completely independent entities. The user gets sort of a hash of these enclaves, and the user can basically sign these enclaves using its own key. So unlike most KMSs which use Intel SGX, we don't sign the enclaves. The customer can sign, they can have their own keys, they can sign those enclaves. And at the same time, they can also verify the software supply chain that we use to build these enclaves. In addition to that, if the customer wants to bring their own set of enclaves, so for example, like in pairing-based system, if you want to have AES 256 level of guarantee, you need like a very high embedding degrees, like embedding degree 48, and we don't support that out of the box. So if someone wants to bring those systems, those kinds of pairing-based curves in the system, they can build their own, and some of our customers have done that and used it that way. Each of these enclaves, which are signed by the same user, they form an enclave set, and they are sort of like a logically isolated entity. So they all have like, so all these enclaves have their own unique keys. For example, they will have like their own TLS keys. And even within these enclaves, there is like a permission system which allows you to like export which keys can be exported to which other enclave. So for example, I may want to wrap an elliptic curve private key using, let's say, Kyber, in which case I will have to transfer that elliptic curve private key to the MLWE module. But you have to give permission to both sides to actually communicate these kinds of information. Each user, each customer gets their own things like TLS, and can't thank like Let's Encrypt for making this possible. So you can just automatically get like certificates for things like that. And each user gets their own access URLs. So two customers, for all intents and purposes with this system, they have like their private instance of a KMS using this system. In terms of cryptographic composition, which I mentioned before, enclaves can talk to each other. So for example, the web gateway can talk to, let's say, different enclaves, which I'm showing here. But all these enclaves have to be signed by the same key. And there is the attestation layer, which makes sure that enclave which is not part of this signed set can talk to this set. And we support, of course, like the TLS v3 with hybrid mode of communication. And using this, you can actually build like pretty sophisticated like ETL and ELT data pipelines. So you can have like a filtering system which is running Python interpreter inside SGX, but it's getting like encrypted data, which is just the session data. It's not all the data, all the keys that you have access to. So this provides like a very strict level of key isolation. In terms of like cryptographic isolation, like per key level isolation, we did not want to have like a master key that most KMSs do. So so in our system, the group of users, like the quorum of users, they fundamentally form the root of trust. So unlike in other KMSs where you have like a domain key or like a root key sitting inside the HSM, individual users, when they sign up with the system, they collectively form like the root of trust. And we also did not want, so we are basically using thresholding, but thresholding has like, traditionally have had like required like a centralized, like either a dealer or you have to have like a distributed key generation for it to work. We didn't want to have like either the distributed key generation and we didn't want to have like any correlated or shared randomness. So what we have like is a very simple scheme. Basically every key that you want to store outside of the KMS, it's split using like a simple linear secret sharing. And each user registers its public key to the KMS. And this public key is used to like encrypt all these shares and stored into the database. And this doesn't scale very well, but this works reasonably well for like up to like 20 people, if you have like a quorum of size 20 people. For larger quorums, we have a system called silent threshold public key encryption, which uses like witness encryption to do the same thing, but without having like a linear blow up in your ciphertext size. So I don't want to go any more details than this, but so I think this is the system that we have, and we do have like a, so you can sign up for like a pre-release demo to test it out. And so that's all I have at the moment. It might be ahead of time, quite ahead of time.
If you have questions, please come up to the mic.
I have a question to ask for. The domain key, is it bound with the hardware for the lifetime, or is it something which is created and administered by cloud administrator?
So it's created inside the HSM, but it's administered through the admin. So the admin has sort of like a black box access to the domain key. And it's synchronized later on, so it has to come out in an encrypted, right.
And your user keys are wrapped in the domain key.
Right, right.
So then my question is,
Can you stay on the mic because it's being recorded?
oh, okay. So the question, oops, okay. So the question is there value to, and are people thinking of wrapping the user keys in the embedded hardware key itself, which is not even accessible to the cloud administrator?
Right, so the domain key is like not accessible to the administrator. So the domain key just has like a black box access, saying that, meaning that you can say encrypt with this key, but I won't give you like access to the, so you have like black box access to the key. And you encrypt the user key using the domain key. Similarly, you wrap the domain key using some mechanism and transfer it across the cluster of HSMs. I don't know if I answered your question.
Sir, in the back.
I'll just try to be loud. Hello? Does your server provide any failover capabilities and high availability type of things?
Right. So because the users are like the root of trust, failover and all these things, so within, if you have like already delegated something in the cloud, these devices can talk to each other using attestation. So once you have delegated, you can talk to each other. But if you haven't talked to any one of these devices, you can talk to like a new device, because all the users, they form the root of trust. So there is like very little communication in terms of like synchronization that happens. I don't know if I answered. So that was one of the design goals, that the end user should be in, if the end user is like the root of trust, I don't need to do like explicit synchronization. If the enclave set, if it's running on like 2 platforms, they can do like mutual authentication using like attestation, and they can synchronize. Or if there is like no entity in the cloud, a user will just go, the quorum will form, and the quorum will provide like the root of trust. So that eliminates like a lot of communication that happens, typically happens by the admin in typical KMSs. Sorry, go ahead.
You talked about software supply of chain not being included in the attestations earlier. So I'm not sure how they're included here.
Right. So basically, we provide like a signature. So you have like a hash of all these enclaves. But with this hash, we also let you have access to the code that was used to build it. And there is like a reproducible build. So Rust provides you with like reproducible builds. So you can take a look at the code. You can look at all the libraries that we are using. You can rebuild it locally on your machine, verify that the hash matches exactly what you're signing, and only then sign and upload it. And we have like tools to do all this. So you can do all of this in like a Docker environment, for example.
My second question would be, you mentioned that you also sort of evaluated current KMS solutions. So are your findings available publicly for anyone to verify or to compare the features that you are providing now against those which are available right now?
Sorry, I didn't understand your question.
So your current evaluation of, current KMS solutions, did you sort of write about them anywhere? Are those findings available on any blog or anything where they can be evaluated against your current offering?
So we will have like a blog post on how this whole thing works. We cannot talk about like what other people are doing like directly, but we will provide a list of things that we are doing and how it differs from maybe like a generic solution. But we will not be, I think we probably cannot legally disclose like what is happening where and things like that. Like if there are like any vulnerabilities and things like that.
Thank you.
So from your description of how this works, once we move to the PQC world, the PQC keygens verifies and will have to be done in the HSM itself, which is puts a hefty hardware requirement on the HSM.
Right. So actually, there are like, I'd say like 2 sides of PQC. One is like support for algorithms, which is like adding support to like Kyber and dilithium. It's like not such a big deal. You're just doing like linear algebra. When HSMs have to communicate with each other, that's what we mean by like post-quantum key management, like that the synchronization and the keys that are stored outside of the HSM, those are like post-quantum secure. So for example, I could have like an elliptic curve key, which I'm storing in the database outside of my HSM. And I need to make sure that even if someone compromises, someone takes a snapshot of my database of my keys, they cannot like reverse engineer and find out the keys.
Let me put my doubt again. Let's assume you need to move the domain key from one HSM of a cluster to another, and you need to wrap that domain key in a PQC key. Where will that PQC key be generated, and can it be generated safely outside without compromising the trust?
Right.
Yeah.
So the way these things work is like the enclaves will authenticate itself, And after that authentication, you have like an ephemeral key encapsulation key, which will wrap the data. So authentication takes precedence. Like authentication will basically ensure that no one else can talk, no two enclaves can talk with each other unless they have like authenticated. And then your MLChem will be basically like ephemeral. So that's all I have. Thank you.
All right, so my name's Loren Shade. We're going to start the last part of the last session of the tracked sessions here at the International Cryptography Module Conference. I always find it industry that interesting that we're at a security conference and then they tape the password to the computer. So anyway, with that, I'd like to invite Dr. Bert Kaliski up to talk about modes of operation for digital signature schemes. Bert.
Well, thanks very much for the introduction, and thank you for the opportunity to talk at the conference. I've really enjoyed the time spent here hearing updates from so many of you who've been presenting and the good conversations in the hallways and over the breaks and so on. Today I'm going to talk about modes of operation, a concept I'm sure you've heard in other contexts, but as applied to digital signature schemes. And you'll see some of the motivations for doing so. So post-quantum cryptography is a theme of this talk, and post-quantum is causing us to challenge assumptions about a lot of things. And one thing are the operational characteristics of the algorithms that we use. I put together some thoughts here because of post-quantum cryptography in two particular ways. One is that it seems that we have some size constraints that may be a challenge in certain use cases. And the trade-off that we appear to be getting for at least the initial generation of post-quantum algorithms, and signature algorithms in particular, is that they're much larger potentially than the signature algorithms we've been accustomed to. So that has presented some challenges that I described last year in my talk on Merkle tree ladder mode for signatures as a way to reducing the signature size. So this gives a more complete consideration of what a mode of operation might be. Secondly, as we've seen in discussions of hybrid or composite constructions, it's now becoming important to formalize how you use two or more algorithms together. And so you could also consider that another kind of mode. So I'll walk through some general thoughts on modes of operation. We'll talk about how the excellent work NIST has done on post-quantum algorithms relates to this modes topic. I'll come back briefly to Merkle tree ladder mode. For the full presentation, you can look at last year's proceedings, and then give some additional modes of operation for consideration. If there are only one or two examples, then maybe we don't have a modes framework to look at, but there are other examples that might motivate you to think about how you would put some design into the modes framework. So we'll start with the modes of operation. I can give a high-level definition that could apply not only to signature algorithms, but to any cryptographic algorithm. It's a way of using a cryptographic algorithm as a component in another cryptographic scheme. So you build one scheme out of another algorithm. Now, of course, that's a protocol in some senses. We're putting together a lot of cryptographic algorithms to achieve some purpose. But when the purpose is an expansion on the initial objective that you had, then you can formalize a cryptographic construction of this type. My earliest familiarity with modes of operation comes from work that was done at the National Bureau of Standards. This was as early as 1981 in Phipps publication 81. The DES mode of operation. So when DES was published, it was a block cipher, fixed key size, fixed input and output size, but there are many ways of using DES, as we become familiar over time, to encrypt messages of arbitrary length. Those were called modes of operation, and there has been a rich history of modes of operation development. In fact, you can look at that as the premier example of modes development, starting with a fixed input length block cipher, which we might now say is the standard being the AES, the advanced encryption standard, and that can be transformed into a variable input length encryption scheme like AES GCM, and would have with other properties like authenticating additional data with it. So over many, many years, I think I've lost count of the number of publications on block cipher mode of operations. But if you look over 40 years of history, you can see how these mature and they're refined, and it's still the same underlying block cipher, but different ways of using it to achieve an application purpose. We could also consider the model like the Merkle-Damgard construction of a hash function from a compression function as a mode of operation. You can prove that your compression function has certain security properties, and then by repeating it, chaining it together, you get an arbitrary length hash function. And you could combine the underlying compression function in different ways. That hasn't been formalized as much. There's the Merkle-Damgard construction I described, but that's another instance where there's a building block that centers the cryptography and then structure around it, which would be a mode of applying it. But this is so familiar as a hash function, we tend not to think of the compression function as the cryptographic internal. And then a hash function itself can be applied in certain modes, and there's a little bit of discussion of this in the literature. The keyed message authentication code, or HMAC, and key derivation functions like HKDF. So these are different additional properties that make assumptions on the hash function, and there are some general characteristics where you could substitute the hash functions and still get the overall objectives derived from what's happening internally. So I invite you to consider signature algorithms in a similar way. If we put in our first column using a signature algorithm, it's a component of something else. What's the larger property that you're attempting to achieve? So the initial focus, at least for this talk and these considerations of modes, is how you might use a signature algorithm as a component of another signature algorithm with additional properties. What might those be? We'll discuss those shortly. It's important that the signature algorithm is used as is. In fact, this is a conversation we can have relative to cryptographic modules. Cryptographic modules will have a standardized signature algorithm in it, and it would be convenient if you can leave the cryptographic module implementation as is and do the modality outside. Now, you could also do the mode inside if you wanted to, but to the extent that the mode itself doesn't introduce additional secret key material, then you could put a software layer around this internal implementation. So message processing is outside the algorithm. What are some of the goals? Well, I mentioned earlier the size constraints in certain applications, DNSSEC being one of those. You want to reduce the burden on different components in the system. So you may want to reduce the burden on the cryptographic module itself if messages get very large, and we'll see the case of the pre-hash mode. You might want to reduce the burden when you're signing multiple messages. If each and every one requires a signature operation, then that increases the size, increases the amount of compute, and maybe you could sign multiple messages, and I'd also consider that a mode, the mode that combines multiple messages into a single underlying component or underlying call to the signature algorithm. And there might be some security goals. The hybrid composite case is one where you're looking for resilience against compromise of a single signature algorithm. So these are the general goals and motivations. So then let's look at very recent examples, and without using the term modes, NIST introduced what I would call two modes of operation for FIPS 204 and FIPS 205 in the initial public draft and in the final publication this year. So in last year's initial public draft, the two modes were called pure and pre-hash signing. I think we all have read of that, we're familiar with that, but it may help to illustrate it here to give you some sense of how the building blocks might fit together. So the pure mode proceeds just as we would expect. There's a message. The message is input to a signing operation together with the private key. Out comes a signature. That's all the familiar part. The pre-hash mode introduced an additional step shown here on the left-hand side where a hash function is applied first, to produce a prehash value, and then that prehash value is input to the signing operation, and everything continues from there. That's been a pattern that's used for a long time. You often will prehash something, maybe it's an attribute of another structure, and that gets signed and so forth. And so these make sense for trading off some of the operational considerations. You could prehash outside of your cryptographic module. That reduces the size of the input to the cryptographic module. That was particularly important if you're making 2 passes over that value. And I could have a longer conversation offline about early designs of the public key cryptography standards that were modeled after tape-to-tape communications in data centers. We were in the 1990s when that took place. You thought, I want to stream the whole thing, so I don't want to store anything in the middle. So the idea of hashing it first is convenient for that purpose. I'll hash it, and then I'll provide the additional operation. So these modes make a lot of sense. The modes as initially specified also introduced one potential for attack. Again, a well-known attack, if you can sign things in 2 different ways, then there's an ambiguity in the interpretation of what you've signed. So drawn here with the arrow going in both directions. Was it a prehash value or was it a message that went into the verification or the signing operation and now is being put into the verification operation? There's no direct way to tell the difference between the two. So it's possible that you could hash a message enough times to find a prehash value that looks like another message that you'd like to trick the verifier into accepting. It depends how much structure there is, how much is allowed to be random, and so on. But you might get the legitimate signer to agree to sign the message by signing its prehash, and then you tell the verifier that no, they actually signed the hash value because the hash value has the bits and bytes that you want. And so you play around with this a bit. I think any system where there's ambiguity in what actually went into the signing operation is vulnerable to this kind of attack. And even back in PKCS 7 and Falco Strenze had a paper just within the last year or so with ambiguity between putting the message in or putting an attribute structure that contains the hash of the message into it. So those are well-known things, as are some of the ways to fix it. So the reason that these attacks have not been more successful over time is that applications have done one of 3 things. So one, you can have an application constraint that says we only support one mode, only one way of formatting the input to the signing and verification operation. If the verifiers only do prehash or only do pure, and the verifier is not going to get confused. You might be more specific about that and say for a given key pair, we only allow one thing, and that could be indicated in a certificate attribute. In fact, that same principle is applied when we're having different algorithms you could use for the same key. And again, that goes back to some of the earlier design days where the certificate said what the key was, but then the choice of the algorithm was up to the application. And now you might be changing your algorithms and therefore interpreting the use of a key in a different way. So by constraining in key usage and being more specific about how the key is intended to be applied, you can also overcome these kinds of attacks. A third way, and the way that NIST arrived at in the final versions of FIPS 204 and FIPS 205, is domain separation. So you put something into the cryptographic input itself that distinguishes one type from another. So all of these 3 have their place. And just to illustrate what came out in FIPS 204 and 205, the one difference you'll see here from the diagram I drew before is this block called the message separator. That's the domain separator. That is a defined value that's prepended to the message when the message is in this pure hash mode. And then in the prehash mode, there's another defined value prepended to the prehash. In fact, you can compare these and see why they're different from each other as long as your prehash separator space is different from your message separator space. Then you will never be putting the same value in for 2 different purposes to the verification operation. There will be no confusion. That makes sense. So that's on the domain separator angle. And being more specific about what goes in the domain separator, we'll come back to some of these later in the talk. The message separator had a fixed 00 byte followed by a context length and a context string. So 1 byte context length, if there's no context, then it's simply a 0 byte that follows. Otherwise, it could be up to 255 with a 255 byte context string. And similarly, in the prehash case, there's the context length, context string, and a hash algorithm identifier, because you want to make sure you know which hash algorithm got input in case there's a break in the hash algorithm. Now you've committed to that as well. So the mode identifier byte differentiates the modes. The context string differentiates interpretation of message by the application in some general sense, the message formats, and then the hash algorithm identifier differentiates the hash function. You can see all these properties. This goes back to early design principles in cryptography. Be as specific as you can about what you're committing to. So the more information you can put in that is explicit rather than implied from context, the better protection that you have from any kind of misinterpretation later on. Right. So now let's look at Merkle tree ladder mode, not in any detail, but showing how it fits into this model. So if you remember from either what you've read or from last year's talk, Merkle tree ladder mode is a way of using a Merkle tree to authenticate multiple messages or data values. I've drawn here the structure that's in Merkle tree ladder mode. In fact, it is multiple trees, so technically it's a forest. And as new data values or messages are added to the right, then new trees are built on top of them. Once you reach the same height for two adjacent trees, they're merged together, and so on. We call this binary rung strategy. There's other terms in the literature, like the binary numeral tree, history trees, Merkle mountain ranges, and so on. So the concepts been published in these other references, but the particular application to digital signature scheme, something we considered new as part of our Merkle tree ladder mode work. And the reason for doing this is to reduce the operational impact of signing messages, particularly when your signatures can be large or expensive. So the use case at VeriSign we were motivated by was the domain name system security extensions. In that case, you have perhaps 100-byte long messages that are being signed, and you've got maybe millions of these that are hosted in a name server or in a cache. And if your signatures happen to be 10,000 bytes long, that means that 99% of your storage and your communications is for the signatures, and the other 1% is for the message. That seemed imbalanced in terms of the scale out of these kinds of systems. So we said, what else could we do? Merkle tree constructions are helpful in this case because you can then sign a large collection of messages, publish the signature once for that large collection, and then for each individual message you publish the authentication path through the Merkle tree, which is relatively short and on par with the size of the traditional pre-quantum algorithms. So you'll see Merkle tree ladders and Merkle tree modes and so on, Merkle tree constructions appearing. The ladder, by the way, consists in this case of the roots of each of the trees. We called it a ladder because it's a way of climbing this upside down tree to be able to reach something that authenticates all of the nodes. And I showed the ladder on the left. So the reason I bring this up here is because we called it Merkle tree ladder mode of operation. Well, how does it fit into the present context? Well, the model we have now for Merkle tree ladder mode is to put multiple messages in. I've drawn them message n+1 through n+k, and these get added into the current state, and then that produces the Merkle tree ladder, which then goes into the signing operation. So you recognize the familiar pattern, just like prehash has some processing on the left that goes into a signing operation. We now have Merkle tree ladder state and processing and so on the left-hand side, and something goes into the signing operation on the right-hand side. And so then that raises the question, what if you were using the same key pair for both signing Merkle tree ladders and signing hashes of messages or signing messages directly? There's a conflict, potential for misinterpretation. Did I sign the actual message or its collection of messages, or was the Merkle tree ladder itself the message that I meant to sign? And so you need to disambiguate that, and we propose to do a Merkle tree ladder mode separator shown in the prepending of the Merkle tree ladder itself. So what did that look like? We have an internet draft. In fact, for completeness, if you go to the IETF website, there's an internet draft. There's several others. One that shows how to apply to DNSSEC, one with general considerations. We have an intellectual property disclosure for a public royalty-free license for certain intellectual property to this. All of that disclosed in IETF. But one thing we did in the most recent draft is we said, if you're using Merkle tree ladder mode, let's use a domain separator that looks like the domain separator that is defined in FIPS 204 and 205. And we thought in typical number allocation convention, we'd use the upper half of the values. So whereas 0, 0, and 0, 1 bytes were already reserved, in FIPS 204 and 205, we thought, let's go to 81 hex. No one will get there anytime soon. We'll reserve that for experimental purposes, certainly subject to change. But that gives another opportunity to distinguish. So if, in case you happen to be using these underlying algorithms in pure prehash mode, then Merkle tree ladder mode would be different. Now, that was an initial proposal. I have some feedback that says there's probably a better way to do that. But here you'd have 81, you'd have a context length, like before the context string, and then a Merkle tree ladder mode algorithm identifier, because there might be different ways of forming your ladder and hashing and so on, just like there are different ways of pre-hashing. Okay, so far so good on that. So differentiation takes place. This is the context separation. When I presented this at IETF a few weeks ago, Scott Florer made a very interesting suggestion. He said, you also have a context string. And so to paraphrase from what we hear in the world of AI, context is all you need. If you have a context string, you have many ways of distinguishing things. You don't need to define another byte. So an alternative to the 81 byte that I proposed would go back to the 00 byte for the pure mode, and then within the context string itself, per Scott's suggestion, define that I'm using Merkle tree ladder mode with this particular set of algorithms, or what the message itself has as its format, and so forth. In other words, the application is then saying, I am directly signing something, but the thing I'm signing, I've already pre-processed. I'm directly signing the result of doing some operation. So that means the application might sign a lot of different things. One of the examples that has been on mailing list discussion recently is applications might sometimes sign certificates and sometimes certificate revocation lists. And those two structures are not necessarily from distinct encodings, because they're objects that were developed for their own particular purpose. So if you have an application that signs a lot of different things with the same key, and you don't necessarily have a way of distinguishing those from each other because their own representations are what they are, this gives you a chance to distinguish it. The context string can say, in this application, here's what I meant to sign. So by extension, if your application is using Merkle tree ladder mode or any other mode of operation, it can do the processing it wants to, come out with a result, and then drop that one into the underlying signature algorithm. And the way it distinguishes one form of processing from another can be by the context string. Now that seems easier than it may be to specify, because it opens the question, how do I define my context string? I've got up to 255 bytes. Who's defining these things? Is it me in the application that enumerates the different bytes? If I want interoperability with different applications, do I need to say the name of my application? If I have different messages that got put into the pre-processing, then do those messages also need context to say what the messages were? And if I'm layering one signature algorithm on top of another, as in a hybrid construction, and they both support context, how do those contexts relate to each other? We posed some questions along these lines to the LAMPS working group. We've also raised a question with CFRG in IETF. So someone should be thinking about these things, but it's good to have these things in place. Okay. So let me turn to one more area for illustration and show you some other examples of signature modes, just to illustrate the variety of approaches you can take. So one I've already alluded to is the composite signing mode. And in composite signing, you pre-hash the message and then sign it with two underlying signing operations, maybe a traditional and a post-quantum. And the design that's in the current draft says we'll pre-hash once, so we don't have to hash the message two different times for the two different underlying signing operations. And then whatever the signing operations do, they're going to do. But to commit to that particular pre-hashing and combination of signing operations, there'll be a composite separator prepended to the pre-hash value. So that composite separator will make clear we did this hashing beforehand and we're going to do these underlying signing operations afterwards. So if there was something different, then we get different values going. And there's no ambiguity about what was meant by the signer in combining these two things. So I consider that a mode of operation. It's a mode of operation of two signature algorithms. What's notable about this particular mode of operation is that there's no context string in it, in the draft. So that was one of the comments made back to LAMPS. The underlying signature algorithms, at least the post-quantum, might have a context string. And so how does that relate to the logic of processing the message when you're not presenting it directly to that underlying signature algorithm? Should this construction itself have a context string as well? Because you want it to fit the API that the post-quantum algorithms fit. So this whole inclusion of context string opens up new possibilities. Just to give you an example from the document, the current composite separator that prepends the hash is a identifier for the combination of the hash function and the two algorithms. So it might be this ID MLDSA44 RSA 2048 PSS SHA-256. And if you can read all of that, you belong at this conference. So that's the kind of thing we talk about, that's the maturing of the state of the art and so on. But there's no context string. I'll give you a few other examples, and I've raised these in some comments sent to NIST on FIPS 204, 205 from VeriSign. So sometimes it's nice to randomize your hashing operation. That's an additional protection. Now maybe this is because I did my work in cryptography when hash functions kept being broken and collisions were found, and so it may be an overreaction to that, but thinking, well, what if there were a collision found in the future for the hash function? That collision could have universal impact, because any two messages that are hashed together that have the same hash value, regardless of the place that hash value is used, that collision would still be applied. A signer can protect themselves by introducing randomization. And they could do that by having a randomizer in the message itself, so that no one doing a collision attack previously would know what your randomizer is. They could come after the fact and try to do a second pre-image, but they wouldn't be able to do a collision attack in advance, or their work wouldn't target you. So what if there were a mode of operation where a randomizer were a standardized part of it? Then you need some mode separator maybe for that pre-hash value, and you put the randomizer in place. Similarly, the concepts of multi-user security suggest that if you're hashing, it's helpful to include the public key or some other user-specific item in the input, because now any of the pre-work that's done by an adversary has to be targeted to that specific public key. One reason I've brought up these comments is that there's so much attention to randomization and multi-user security in the underlying signature algorithms. Like Sphinx Plus, for example, was evolved over several iterations to make sure that all these inputs were included. So then if you do a pre-hashing operation mode, you give up some of those advantages that you had in the underlying algorithm. So this is a way to restore the advantages by putting in the public key, or putting the public key in a randomizer. Well, those are all different modes. And I'm not advocating that any of these is necessary to standardize or implement or so on, but when applications start to think about them, they've created a new mode. And is that something that the application itself would do by formatting the message in a certain way? Or should there be a more common specification for doing that by saying this is a mode, let's standardize it and let's put it on top of the signing algorithm? All right, so in conclusion, you can read the slides later when they become available. What you can see is there are a lot of different examples of mode where I started with pure signing and pre-hash signing, the initial ones proposed by NIST, the final ones with their updates, Merkle tree ladder mode, and the composite signing, and randomized, and so on and so forth. What else is there on this list? How do we want to think about that? Where do we want to get this kind of work done? There's some security and operational advantages to doing what I've described. How can industry work together? It has does it done successfully in so many other areas. And so I invite any interest in collaboration and feedback, jointly writing specifications and standards bodies and so forth, and I welcome your questions.
Hi, Bert. Oh, is this thing on? Hello, okay. Yeah, thanks for that presentation. I just wanted to make a comment. We are working on adding the context string now into the composite signatures based on probably that was you that put that there. We had a discussion about that last week. We have 2 proposals, so we're still thinking about it, but probably the next few weeks we'll be publishing an update before the next IETF that will contain that. So thank you.
Okay. Thanks, John. Yeah, so follow up in LAMP's working group.
Different question. Do you feel that the domain separator is enough of a separation, or would you still recommend the principle of one key, one purpose?
I outlined three ways of achieving the goal. I think the domain separator is a good starting point, but you then introduce the complexity that you have all the different choices you can make. So it may be easier for some applications if key management or application constraints say, this is the only way we're going to do it. Because it's hard to predict over the life cycle of an implementation or protocol what will happen, it's nice to have both protections available.